All right, my friends, let's play with these partial sums and then we'll get to what the heck the remainder theorem is saying. So first partial sum would just be the first term, so -1. Second partial sum would be the first plus the second term, so it looks like that would be -1/2. The third partial sum, we'd have to subtract in that 1/3. I'm going to start switching to decimals, so we'd get -0.83 repeating, it looks like. Fourth partial sum, let's add in 0.25. We've got -5 whoops, the 5 is not in front of the decimal. 0.583 repeating, and then we'll subtract off the 1/5. Lots of 3's repeating. Anyway, and then let's add 1/6, for the next one. Oh, there we go. We got a 6 repeating now. That's exciting. Okay. So I hope it makes sense that as we bring in more terms, I would say we're closer to what the actual sum is. And so as we add in more terms, we're kind of like less wrong, or we're reducing the error. So now let's talk about how wrong are we and how could that help us? So first let's talk about this first partial sum. And I hope it makes sense. We're probably pretty wrong if we've only used the first term, because we'd have all of this remainder. And so some notation, if you have a first partial sum, the rest, which actually starts with the second term, would be considered the R sub 1 means the rest after the first term. And so that would be the error, right? The rest, the stuff we didn't add in. And so, but I want you guys to look at this error, right? 1/2, take away a third, add in a fourth, subtract a fifth, add a sixth. So I hope it makes sense that because of the nature of the numbers, they are decreasing in magnitude, and you are alternating in sign. I hope it makes sense. So if you have, like, imagine half a cup of sugar and then you scoop out a third of a cup. So you have half a cup, you scoop out a third of a cup, then you add in a fourth of a cup, then you scoop out a fifth of a cup, then you add in a sixth of a cup. I hope you can imagine the level of, say, the sugar rising and falling. But no matter how long you stay at that process, you are never going to have any more than you started out with. And so we would say that the remainder is always less than or equal to your first neglected term, which in this case would have been 1/2, or the absolute value of the first neglected term, because if you start off on a negative, you'd want to say the absolute value. So in this case, we would say the remainder is less than that first neglected term. So now let's talk about the second partial sum. So the second partial sum here, so that's S sub 2. Here's your remainder, which we would go ahead and call R sub 2. It turns out the remainder, like how wrong are we, is going to be less than, or actually not even less than or equal to, less than. The first neglected term this time is -1/3, so we would, make sure and put absolute value marks around that. So you'd end up with, 1/3 there. Anyway, so the point is that if you have a convergent alternating series, the remainder, or your error, when you use a partial sum, is always going to be less than the absolute value of your first neglected term. So for S sub 1, now some notation, your error would be the difference between the actual sum and your partial sum. So for example here, R sub 1, which is, all of this, it means the difference between the infinite sum, which, remember, if we don't have a subscript, that means an infinite sum, and your first partial sum. And because we don't know which one is bigger, we throw absolute value marks around it so that it really is the difference. And that would always be less than your first neglected term, which for a first partial sum would be, A sub 2. And then if you used a second partial sum, then the remainder or your error, how wrong you are, would first of all mean the difference between the infinite sum and your second partial sum. And it's always going to be less than your third term, your first neglected term. So now some notation fix here. I should put absolute value marks around this in case your first neglected term is negative. So hopefully that helps. And let's just jump. I don't want to write this for each one, but let's say you're talking about your sixth partial sum. We would say your error, how wrong you are, which means the difference between the actual sum and your sixth partial sum, would be less than the absolute value of your first neglected term. Well, if you used a sixth partial sum, your first neglected term would have been negative 1/7, which in general would mean a sub 7. There we go. Okay, what we're going to do now is we're going to write the remainder theorem in words. You need to memorize the words, and then we are going to write it in math symbols, and you need to be comfortable with the math symbols as well. So here we go. So the words for this theorem are, for any convergent alternating series, the difference between the infinite sum and any nth partial sum is less than the absolute value of the first neglected term. Okay, now, so you do need to memorize this, my friends. It's going to be really important that you have those words memorized and ready to go. Okay, well, you'll see when we start practicing for the AP exam that actually comes up fairly often. Okay, now let's say exactly that, but using math speak. So if you want to find the difference between two things, you subtract them, but then you take the absolute value as well, because the difference between two values is always a positive number. So for example, if I was to ask you, how old are you? And then I tell you how old I am. Let's say you're 16 and I'm 46. Then what's the difference between our ages? Well, the answer would be 30 years. You would make sure the difference is a positive thing. I hope that makes sense. So anyway, so the difference between an infinite sum and an nth partial sum, absolute value marks are necessary, is always less than the absolute value of the first neglected term. Well, if you used this uppercase nth partial sum, then what would the first neglected term be? It would be a sub that number plus 1. There we go. I hope that makes sense. All right. So let's play with this. For example 4, I'd like for you to find an estimate of the value of the sum as n goes from 1 to infinity of negative 1 to the n times 1 over n. It has an error no greater than 0.2. All right, a little tip, if in doubt, expand it out. Good luck.